I'm going to have you vote on it. Is it going to go to negative 69, or is it going to go to negative 71? All right, how many of you vote for negative 69? Ooh, lots of you. Some of you. How many of you for 71? Wonder not so full. All right, so, okay. You got more positives coming in, right? If it becomes more positive, what happens to our negative number? Does it go towards 0 or away from 0? Well, okay, so you've got negative 70. Now here comes another positive in. Well, now the inside of the cell is a little bit more positive, right? In other words, a little bit less negative. Does that make sense? Okay. So less negative would be negative 69. So that's the direction we're heading. All right, so let's get rid of these guys. And so the voltage drops to negative 69. And what's happening is the cell is becoming depolarized. And so we say that we're getting depolarization happening. Depolarization. And so let's suppose that this is a sound waves coming along, and it affects the auditory sensors in your ear. Your eardrum is vibrating, and it sends this little message to your neurons that go to your brain that says there's a sound. And the sound is very, very slight. It only opened these gates a little bit or for a short time. And then the gates snap back shut again. And they will do that because these gates are stimulus gated, and it is a graded response. That is, the bigger the stimulus, the bigger the response. The response being here, how long the gates stay open and how many of them open. Okay, so that first of all, these stimulus gated channels are graded channels, and it's a graded response. The bigger the stimulus, the bigger the response. The response again being how many sodium channels open and how long they stay open. Okay, so here came this very, very faint noise, and it caused just a few of the stimulus gated sodium ion channels to open, and the cell was depolarized to negative 69 millivolts. Guess what you hear? Nothing. As far as your life was concerned, there was no sound. They're there right now, but you don't hear them. Because when the voltage drops to negative 69, that's not a big enough response to send the message down the axon. Remember, that's what a nerve impulse is. The electrical impulse has to travel down the axon. Well, negative 69 isn't going to do it. And so if this were such a slight sound that it only dropped the voltage to negative 69, you're not going to hear anything. And that's a good thing. You don't want to hear everything. There are people who suffer from some of these maladies where they're hypersensitive to sounds and touch and sights, and it drives them crazy because they just hear everything and they feel everything. So that's a good thing that we don't see and hear and feel everything. All right, so the question then is, how far down does this millivoltage have to go in order to trigger a response? And the answer is it has to go all the way down to negative 59. So negative 59 millivolts is what's called the threshold potential. The threshold membrane potential. In other words, there has to be a difference of only 59 millivolts across the membrane rather than negative 70 in order for a nerve impulse to occur. The reason that a negative 69, or the fact that negative 69 does not generate a nerve impulse, means that the stimulus stays in this locality. In other words, it doesn't travel. It stays right here at the nerve, at the cell body membrane, and it doesn't travel. So we say then that this is a local potential. And you don't even know they're occurring. They're occurring all the time in you right now, but you never become aware of them because they're dead ends. They don't go anywhere. So a local potential is graded. That is, the bigger the stimulus, the bigger the response. It's local, that is, it's occurring just on the cell body, and it's not traveling anywhere. Now the local potentials, if they're big enough, they can cause it to travel, but they themselves stay right there. What we've just described is called excitation. That is, you excite the neuron. To excite it, I suppose, means that it's likely to do something. So that's that's called excitation. The reason I bring that up is because just the opposite can also happen. There are certain stimuli that don't open the stimulus-gated sodium channels, but do just the opposite. They make it harder for them to open. All right, so there is a flip side to all of this, in which a stimulus comes along that makes it even harder for the sodium ion channels to open. And so we would call that not depolarization, but hyperpolarization. And you might say, well, why in the world do we want our neurons to be hyperpolarized? Well, there are times when we don't want neurons firing. I'm just thinking of one. I don't know. I haven't actually looked this up, but I think this would be a case where after you eat and you're full, the satiated, we have receptors for that. You don't want anymore. You don't want the sight of food to stimulate hunger pains and appetite. You're full. So your stretch receptors and so on in your stomach would probably hyperpolarize those neurons, which give you an appetite. And that's a good thing. Ellie, you had a comment.
That be a stimulus when neurotransmitters others like something really big. Like
Possibly, yeah. Probably, I would think so.
What happens in hyperpolarization?
In hyperpolarization, the stimulus that's coming in not only doesn't open these, but makes it even harder for something else to open them. In other words, they stay tightly closed, and probably opens more of the potassium channels too, to get more sodium out, or potassium, to get more positive charges out. All right, and so the cell becomes hyperpolarized, and instead of calling it excitation, we call it inhibition. So the green and the black are opposites of each other there. Alec.
Inhibition is just when it's harder for it to
Right, so an inhibitory stimulus makes it harder for the cell to depolarize. In fact, it hyperpolarizes it. And I think that we probably should add that it would hyperpolarize it by actually opening some of the potassium channels and making it even more positive on the outside. All right, we're going to have to quit here.